Hello everyone, welcome to lecture 10 of the course on entanglement and non-local games. Today we look at games which require an infinite dimensional of entanglement. Now, what does this mean? So until now we have seen games like CHSH game, the magic square game, right, wherein we had two parties and they were given classical inputs, they needed to produce classical outputs, and in such a way that their outputs should be correlated in some form. Now here, so for CHSH game you saw that having one EPR pair suffices. For magic square game, two EPR pairs sufficed. But are there games which require, and so over there you could see that the amount of entanglement was finite. So the question is that, are there games which require an infinite amount of entanglement, right? So do we need games wherein we need entanglement in infinite dimensional systems? So the answer is indeed yes. And today we look at one such game. The form of this game is slightly different from what we have seen so far. This is because the game which we'll see today is of the form of quantum input game, right? So here basically the inputs to the two parties, Alice and Bob, are also quantum states. So let's see what a quantum input game is. So here the setting is as follows. So inputs to Alice and Bob come from a subset of quantum states ket phi 0 up to ket phi m minus 1. Here each of these states, ket phi I, is a state in space CL tensor CL. So basically the inputs to these players are indeed quantum states, and these states are entangled between them, and these are given as input to the two players. Now what are the outputs here? The outputs are same as before, that is they have to be classical bits. So these are classical strings or bits A and B. So this is the output of Alice, this is the output of Bob, right? And let us say that these come from the set A cross B. So here we will actually consider that Alice and Bob are allowed to share some entangled state psi AB. So this is something they are sharing between them, and phi I is the state which they are given as input, right? And so here let's see an example. So here let's see an example wherein Alice and Bob, they share so suppose they could be given one of these two inputs, phi 0 or phi 1, where phi 0 is of the form 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB. So this is the regular EPR pair, and phi 1 is also one of the Bell states, but here it's a minus sign. So let us say that these are the possible inputs to Alice and Bob, right? So basically these states are shared states, okay? And what they have to do is that they need to produce a bit each. So let's write. So Alice needs to produce, so Alice and Bob, these are the two players or two parties, and they are given one of these inputs, phi k, phi 0 or phi 1, and Alice needs to produce a bit A, Bob needs to produce a bit B. Both of these are 0 1 binary variables, bits, and the winning condition here. So what's the winning condition? Winning condition is that A XOR B, this is going to be 0 if input is ket phi 0, and 1 if input is ket phi 1, right? So here basically these are the winning conditions, that that A XOR B, if you are given phi 0, if they together receive phi 0, then basically they should produce equal bits so that their XOR is 0. If they receive ket phi 1, then they should output unequal bits whose XOR is going to be 1. Now the thing is that firstly the question is that can Alice and Bob independently figure out whether they have received ket phi 0 or ket phi 1? So question, can Alice or Bob independently figure out if it is ket phi 0 or ket phi 1? So this is the question, right? Can they do that? And the answer is, well, no, right? Because if you take the reduced density matrix on Alice, right, it's going to be I by 2, independent of whether it's phi 0 or phi 1. Right? Similarly, the density matrix on Bob is also going to be I by 2, independent of whether they have whether they received ket phi 0 or ket phi 1. So check that. So here basically, since it is independent, so here the state in fact does not have enough information, but they can actually still win the game very easily. How? They'll just need to measure their state in the Hadamard basis, the plus minus basis. And so let's see the winning strategy. It's a very simple winning strategy. And in fact, you can see that they actually don't need any entanglement at all for this, right? So the answer is that measure your state, measure your received qubit in Hadamard basis, right? So Hadamard basis meaning that plus minus basis. This happens to be the eigenstates of x, okay, the operator x. So how? So for phi 0, so for ket phi 0, we can check that minus 1 to the power a XOR b, because see, the eigenvalues are plus minus 1 instead of 0, 1. So here the so if both of them measure state in x basis, they actually measure this observable x tensor x, and the expected value of this will be minus 1 to the power a XOR b, because we are looking in the plus minus 1 regime, right? So here they are multiplied, and whether you take the bits and take their sum, or whether you take plus minus 1 variables and take the product, it's going to be the same. So here this is going to be the expected value, and you can check that for phi 0 this will come out to be plus 1, so which means that a XOR b is going to be 0. Now let's look at the case when they have received ket phi 1. So for ket phi 1, we have that minus 1 to the power of a XOR b. Okay, this is going to be ket phi 1 x tensor x ket phi 1, right? So you can actually again substitute the state for ket phi 1, and you will see that this is going to be minus 1, which means that a XOR b is over here is going to be 1 instead of 0. So here basically they are going to win the game with probability 1, and they didn't need any extra entanglement, right? Whatever state they received, ket phi 0 or ket phi 1, they just made a local measurement. So here basically no entanglement was needed, right? And actually I promised you that I'll tell you about a game which requires infinite amount of entanglement, but I've given you a game wherein the players can win without any form of entanglement being shared. So but actually we'll expand upon this game. I'll describe a newer version of this game wherein indeed one will require an infinite dimensional of entanglement to win the game. So no entanglement needed. So now let's see the game, the actual game with infinite dimensional entanglement. So here the inputs to the two players, instead of being qubits, they are going to be qubits, and the outputs are going to be bits. So here let's see what are the input states that are possible. So here basically we could have had a state cat phi 0 or cat phi 1. So cat phi 0 is described as 1 by root 2 0 0 plus half of cat 1 1 plus cat 2 2 AB, and cat phi 1 is 1 by root 2 0 0 minus half of cat 1 1 plus cat 2 2 AB. So you can see that the state looks very similar to what we saw earlier, right? So these are the possible inputs. So earlier what we had was these two bell pairs, right? So here we had either plus or minus over here, but now it's just that cat 1 1 is itself replaced by another EPR pair on 1 1 and 2 2. So the winning condition is the same. So the winning condition is that A XOR B must be 0 for cat phi 0 and 1 for cat phi 1, right? So here we indeed state our first theorem. So what does this theorem say? This says that for any epsilon greater than 0, there exists an entangled strategy that succeeds with probability greater than equal to 1 minus epsilon. Secondly, the local dimension D of entanglement to obtain the success probability greater than equal to 1 minus epsilon, okay, will tend to infinity as epsilon approaches 0. Okay, so we'll see that it should be, at least of the order of exponential of 1 over root epsilon. So that we'll see. So in order to show the above, we'll actually define a new notion, which is the notion of embezzlement, and then we'll show that that there is indeed that embezzlement is indeed possible, and that there is a lower bound on the strategy for getting an embezzled state, and then we'll show the equivalence between embezzling strategy and winning this game. So to show the above. So firstly, we'll define a notion of embezzlement of entanglement. Secondly, we'll show the existence and dimensional lower bound for embezzling strategy and thirdly we'll show equivalence between embezzlement strategy and winning strategy for above game. So actually in today's lecture we are going to look at these first two, and this third part we look in the next lecture. So firstly, I haven't even told you what is entanglement or what is embezzlement, so I'll just do that now. Okay. So what is embezzlement? So the idea is as follows, that suppose Alice and Bob, they share the state cat 00 tensor psi AB. Okay, so can they perform local operations? Local operations meaning that they can perform a unitary operation on their share of qubit, or they can perform a measurement. So can they perform local operations to obtain the state EPR, that is 1 by root 2 0 0 plus 1 by root 2 1 1 tensored psi AB, right? So psi AB is like a catalyst state, so that should remain the same, but it should assist in moving from cat 00 to 1 by root 2 cat 00 plus 1 by root 2 cat 1 1. So the question is that, is it even possible? And the answer is no, right? This is because this cat 00 state, this has entanglement entropy of 0, whereas this has entanglement entropy of 1 bit. And you can't, local operations cannot increase entanglement entropy, right? So they can only decrease, or they can make it the same, keep it the same. So yeah, so this is something we cannot do, right? But what we can actually try to do is that we can try to achieve this sort of a state with some fidelity using local measurements, and that amount of fidelity will describe, how much is the embezzlement we are performing. So let me write down the formal definition. So for epsilon greater than 0, right, or greater than equal to 0, so obviously epsilon here is less than equal to 1. So for epsilon between 0 and 1, and epsilon approximate embezzlement strategy is a triplet UA, UB and psi AB, such that the fidelity between cat phi idea, which equals 1 by root 2 0 0 plus 1 by root 2 1 1 AB, okay, tensored psi AB and phi actual, which is produced by UA tensor UB on cat 00 AB tensored psi AB. So essentially what the thing is that psi AB is like a catalyst state, and you want to start from 00 tensor psi AB. You want to apply the these UA tensor UB. So these are local operations which Alice and Bob are performing, local unitaries, and we want to achieve the state of EPR tensor psi AB, right? And with fidelity, yeah, so this is the main catch here, with fidelity greater than equal to 1 minus epsilon. So note that we are not saying that the fidelity has to be 1, right? So we are only saying that it has to be greater than equal to 1 minus epsilon. And so So here the dimension of psi b is the entanglement dimension. So let's see, okay, the strategy for embezzling such a state. So we'll see that we'll need this. So we'll actually need an order 1 over epsilon number of qubits. So let's see. So here is the strategy for. So we have seen the definition. Now look, we are looking at the second part, which is the strategy for embezzling. 1 by root 2 0 0 plus 1 by root 2 1 1. So here let m be a natural number, okay, and then for k in the set 0 up to m, we define get theta k to be cos of pi k by 4m 0 0 ab plus sine pi k by 4m 1 1 ab. Okay, so here we are going to define theta 0 to be ket 0 0, and we are going to go up to theta m, which is going to be 1 over root 2 0 0 ab plus 1 over root 2 1 1 ab. Okay, so here let's look geometrically what is happening. So we have these basis states which are spanned by ket 0 0 and ket 1 1. Okay, and we have all these vectors. The kth vector theta k makes an angle of pi k by 4m, right? Between theta k and theta k plus 1, the angle is going to be pi by 4m. Okay, so then we see that the inner product between theta k and theta k minus 1, right? So this is going to be cos of pi over 4m, right? And you can check that cos x is like, you can use the Taylor series and you can check that this will be greater than equal to 1 minus c by m square for some c. Actually, you can just use that cos x is greater than equal to 1 minus x square by 2. So that should work for you. And yeah, you can prove it using Taylor series or any other approach also. So here essentially we see that between the two consecutive vectors, the angle which is made is greater than equal to 1 minus c by m square. And now we are going to define the local operations. Suppose, so here, suppose Alice and Bob they share the state psi e equals to theta 1 ab tensor theta 2 ab tensor theta m ab. So note that I am not writing theta 0 over here. So theta 0 is just ket 0 0, which is their initial state they are given, and this is the state, the resource state which they are sharing. So now we define the local operations ua and ub. As right cyclic shifts, right cyclic shifts. Okay, so we define ua of x0 up to xm a to be equal to xm followed by x0 up to xm minus 1. And similarly for Bob also we define the corresponding ub. So essentially it's nothing but everything shifts to the right and then cyclically xm comes to the front. So these are the local operations they are going to perform. Now let's see what happens when they perform together this UA tensor UB on 0 0 tensor psi. So UA tensor UB, so 0 0 was their input state, right? They want to embezzle, and psi is the resource state they are sharing. So when they each perform their local operations, this is like acting UA tensor UB on, so this is nothing but, so this is nothing but the state 0 0 AB tensored theta 1 AB tensored up to tensor theta m AB, and 0 0 is also nothing but theta 0 AB, right? So here when they perform this right cyclic shifts, so everything moves one step to the right, and what you get is theta 1 AB tensored, it has to be theta m AB tensored theta 0 AB tensor theta 1 AB into tensor theta m minus 1 AB. And theta m is nothing but 1 by root 2 0 0 plus 1 by root 2 1 1. So 1 by root 2 0 0 AB plus 1 by root 2 1 1 AB, and then this whole thing is tensored with the state psi prime. So psi prime is nothing but this state theta 0 up to theta m minus 1, right? And what we can actually check is that the fidelity between psi prime and psi is going to be what? So basically psi was supposed to be theta 1 up to theta m, and this is theta 0 up to theta m minus 1. So here you can see that this is theta 0 dot theta 1 times theta 1 dot theta 2 up to theta m minus 1 dot theta m. And the angles between each of these we have seen is nothing but cos pi by 4m. So this is going to be cos pi by 4m to the power of m, right? And this is greater than 1 minus c by m square to the power of m, right? Which is greater than 1 minus order 1 over m, right? So you'll have to use that identity that 1 minus x to the power n is greater than equal to 1 minus nx. So just check that. So basically in order to receive fidelity, greater than equal to 1 minus epsilon, it suffices to choose m as order 1 over epsilon. Okay. So here we have seen that the local dimension of the catalyst is going to be 2 to the power order 1 over epsilon. Right. So basically this much indeed suffices. So this is the dimension of the Hilbert space, that so essentially you need m shared qubits, so which is like order 1 over epsilon shared qubits, and exponential of that is the dimension, right? So here basically the entanglement so the entanglement cost or the entanglement dimension of embezzling the state up to epsilon fidelity is 2 to the power order 1 over epsilon. Like basically this much is sufficient, right? So this is the sufficient dimension. Now we will actually show that it's necessary to be exponential in order 1 over root epsilon. So this is the next claim. So in order to get fidelity epsilon greater than 0, we must have d local as exponential of omega 1 over root epsilon. Okay, and now we are going to see the proof of this claim. This proof is based on Fan's inequality. Fan is inequality. So I'll just state this inequality. You can see the statement, the full proof and all in Nielsen and Chong's book. So let's see what is this inequality. So this states that for density matrices, rho and sigma, which are both d cross d dimension, we have that S rho minus S sigma is less than equal to delta log d plus order delta log 1 over delta. Right. So here S is the von Neumann entropy, and delta is the trace distance between rho and sigma. So trace distance is essentially the maximum amount of so basically it's the maximum amount of distinction which I can obtain if I measure these two states. So basically this is the probability of success kind of if I want to distinguish between these two states. And so this is essentially the Fan's inequality. So here the what it says is that as a function of the trace distance, entropy is continuous in entropy is a continuous function of rho in terms of trace distance, right? So suppose if the trace distance goes to 0, right? So if delta goes to 0, then the difference in entropies will also go down to 0. So this is what it says. So this trace distance can be considered as a metric, and on this metric it is a continuous function on the space of density matrices. Also what we'll need is a relationship between trace distance and fidelity. So this is the relationship. Again, this is also given in Nielsen and Chuang book. So and fidelity. So let me write down. So the relationship is that 1 minus the fidelity is less than equal to trace distance, which is less than equal to square root of 1 minus f square. Okay. So basically, if we are given that that between two states rho and sigma, if the fidelity is greater than equal to 1 minus epsilon, then it immediately gives us that the trace distance will be upper bounded by, so suppose if fidelity between rho and sigma is greater than equal to 1 minus epsilon, then the trace distance between them is going to be less than equal to 1 minus epsilon square, which is less than equal to square root of 2 epsilon. So we'll actually now use this. So let's see. So here the idea is that, okay, so suppose if I have this state psi tensor 0 0 0 0, the entropy of this is going to be the von Neumann entropy of just psi. Okay, and the von Neumann entropy of psi tensor 1 by root 2 0 0 plus 1 by root 2 1 1 1 by root 2 0 0 plus 1 by root 2 1 1. Okay, so Okay, so suppose if I define this type of a matrix, then basically this entropy is going to be 1, which comes from here, plus the entropy of S of psi psi. So essentially, if I have 0 0, I'll have some entropy, but if I have this EPR pair, then the entropy will exceed by 1 unit. And here, so basically this is something I'm going to call rho. Let me call this sigma. So essentially what I have seen is that S rho minus S sigma is going to be 1. Okay, and this is going to be less than equal to delta times logarithm of d plus order delta log 1 over delta, right? So here we have seen that the trace distance between them was at max order root epsilon. So here basically this is going to be less than equal to root epsilon log t plus root epsilon log 1 over root epsilon, and so and up to order notation, this is root epsilon log d plus root epsilon log of epsilon. So there is a factor of half which I am not writing here, but you can see that this approaches 0 as epsilon approaches 0, whereas this term approaches 0 as epsilon goes to 0. So basically this is the dominant term, and here in order to get this equal to 1, we must have that log of t to be at least 1 over root epsilon or d to be exponential of 1 over root epsilon. Okay, so yeah, so essentially what we have shown is that the dimension should be at least exponential of 1 over root epsilon, and we have also seen that having exponential of 1 over epsilon suffices, right? So essentially we are always working in this exponential size dimension, and yeah, and this is almost necessary and sufficient as well. In the next lecture, we will see that how this embezzlement thing relates to our quantum input game, and that will actually prove that the existence of a game wherein in order to get better and better sort of winning probability, we will need larger and larger dimension. So the ideal amount of dimension will go up to infinity. So that's now the goal of the next lecture. Okay, thank you. Bye.